Hello, VC. I thought I'd do a couple problems on a short little screencast. I know we didn't have quite enough time today after the quiz. So I first wanted to work through 18, right, which is saying that I want to have the closed sum. Remember, that's without a summation notation of this guy. So we're going to go from k equals 1 up to n minus 1 of k squared over n. And notice here, right, when I have something that looks like this, only one of these two guys, k squared or n, actually depends on the thing that we're indexing, right? N is sort of above the fray, and it's independent of what we're subbing in, right? We're subbing in for k for all these values, for 1, for 2, for 3, for 4, all the way up to n minus 1. So n on the inside is sort of independent, so we can actually pull that out. Remember, if we have some constant that's independent of the k, we can pull that out. So we can say first off that this thing is really 1 over n times the sum of k equals 1 up until n minus 1 of k squared, right? Because again, the n is above the fray, it doesn't matter, right? It's sort of like if we had over 2 there, right? We can pull it out. So now we really just have this k squared, and recall from class, right? Recall that we had, sorry, I have a little cough, this form of if I have k equals 1 up until n of k squared, right? Recall this is where I made the small boo-boo in class, right? The small boo-boo in class, right? This is really just n times n plus 1 times 2n plus 1. Remember, I had a 6 there by accident, all over 6. So I can do the same thing here, but instead of plugging in n, instead of plugging this n in, we're going to need to plug in n minus 1. So we're going to sort of have to re-index ourselves. So going back up here, right, this is still 1 over n, and then now I can have this closed form notation. So instead of n as the first guy, I want to have actually n minus 1. Instead of n plus 1, I would have n minus 1 plus 1, which of course is just n. And then instead of 2n plus 1, remember I'm plugging in n minus 1. So I'm going to get 2 times n minus 1 plus 1, all over 6. Now, of course, these n's are going to cancel, right? So I'm going to be left with n minus 1 times this thing, times this thing. So that would be 2n minus 2 plus 1, 2n minus 2 plus 1, all over 6. So that's n minus 1 times 2n minus 1 over 6. And I cannot do anything else. So this is the first of our two problems that we're going to do together. The second one's going to be very similar to the one that we have in class. If you hear my wife and daughter in the background bickering about something, I'm sorry about that. So let's consider one of those area problems. So let's suppose that we wanted to find the area under the curve 16 minus x squared. That's sort of my f of x. And I wanted to find that on the interval of 1 to 3. 1 to 3. This is a little bit trickier than the one we did in class, but we can certainly draw it, and we could take a definite integral. And then from there, we can do our infinite sum. So 16 minus x squared, right, so the downward-facing parabola. Its y-intercept's up here at 16. And obviously its x-intercept is going to be down here at 4, right? So it's going to look something, very, very bad drawing to start, right? It's going to look something like this, right? And we are concerned with this area between 1 and 3, 1 and 3. So we can draw this, and we're concerned with this shaded area between the x-axis, the curve, and the line x equals 1 and x equals 3. Okay, so first let's find it with a definite integral. Okay, the definite integral, okay? And so that thing goes from 1 to 3 of 16 minus x squared. And I'm told that I have to vacate this room, so hold please while I just move very, very briefly to a different room. Can't wake the kids, of course. So, sorry about this. We're looking at this definite integral from 16 minus x squared from 1 to 3. Of course, that is dx. 16 minus x squared x. And now, by now, we're all pros at this, right? So we're just going to integrate this right away, right? Sort of the reverse power rule. We get 16x minus 1/3 x cubed, evaluated at 1 and at 3. And remember, that's the value at 3 minus the value at 1 of this integral. So what is that? 16 times 3 minus 1/3. What is this? What is this 3 down here, right? This is x cubed. 1/3 3 cubed minus this whole thing, 16 times 1 minus 1/3, 1 to the third. So what is that? That's 48. This is a 9. This is a minus 16 minus 1/3. So that's really, help me out here. 39 minus 16 plus 1/3, or 23 1/3. Seems maybe feasible, right? That'd be a width of 2 and a, average height of about 11. Yeah, I buy it, right? Makes sense, sure. It's definitely a plausible answer as opposed to something, if we got like 85, that would, definitely not be true, right? But would you believe that this thing has an average height of 11 ish, a little more? Yeah, sure, right? It's obviously going to start a little bit slow. So we found our answer. Let's see if we can find a sum that will match that. Okay, so remember from class that we started, I don't want to lose all of this work, but we're going to lose some of it as we sort of progress down. So let's talk about, we wanted to draw infinitely many of these tiny, tiny little rectangles, right? Obviously my thing has a lot more width than the actual guy, right? I remember we had infinitely many of them, and their width was some delta x, right? Delta x was a width, and the height was our f, right? Whatever we were at some high point for each of the k rectangles. And we're going to, again, use a right-hand sum because it's a little bit easier to wrap our head around. Okay, so we're again looking at this guy. The limit as n, I want to be back in the black color. We want to look at the limit as n approaches infinity of some sum. And what sum is that? That's as we go from k equals 1 up to n of that height, right? Whatever our function is for the kth rectangle times that delta x. Okay, well, we know what some of these things are, right? Delta x, we said, right? This is our aside, right? Our aside box. We know that delta x is how many. What's the total width? The total width is 3 minus 1, right? And I have n of these rectangles as n goes to infinity. So each rectangle is 2 divided by n wide, right? Each one is 2 divided by n wide. And if I had to talk about the height here, right? What is my x coordinate? Remember, we'll take f of that. What is my x coordinate for the kth rectangle? What is my x coordinate for the kth rectangle? Well, all of my rectangles sort of start at 1, right? Because we didn't consider anything in here from 0 to 1. So they all have to start with 1. And then each time, if I'm on k rectangles, I've moved k times delta x over. K times delta x over, right? Because for each rectangle, I moved delta x. And I've done that k times to get to the kth rectangle. So this is the x coordinate of my kth rectangle. So now let's plug some of those back into here. So this is my little aside over here that we're going to use. So if I want to consider this new limit that we just saw, the limit as n approaches infinity of the value of my function, of the sum of the value of my function for the kth rectangle, that's the height, times the width, delta x, we can do a lot of substitution in here, right? Well, I know what each of these things are. So this thing, I'm going to move over here. This thing is the limit as n goes to infinity, again, of this sum, k equals 1 to n, of f of, we know what that is now, 1 plus k delta x times delta x. Okay, well, I know what f is, right? F is 16 minus x squared, so I can literally plug this value into 16 minus x squared, right? So that's just equal to the limit as n approaches infinity of 16 minus this thing squared. 16 minus this thing squared, all times that delta x. All times the delta x. Well, we can FOIL this mess out. We can FOIL this out very easily, right? This is just the limit as n goes to infinity of the sum. Oops, forgot my limits here. K equals 1 to n. K equals 1 to n of 16 minus 1 plus 2 k delta x plus k squared delta x squared. Again, all times delta x. Well, this thing looks pretty messy now. It looks pretty messy, but we're going to clean it up very, 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 very fast, I promise. Okay, so I'm gonna combine some like terms, and I'm gonna split this into several smaller sums. Actually, yeah, let's do that. Okay, so this is, well, we'll do one step before. Oops, forgot my limit. This is the limit as n goes to infinity. Again, of my sum. And in here, I'm going to start plugging in for delta x. Remember, delta x was 2 over n. We found that in that blue box up there, right? Delta x was 2 over n. So this is 15. Maybe we'll do one. Well, 15 minus 2k times 2 over n minus k squared times 4 over n squared. Remember, we have this delta x squared over here. Again, all times 2 over n. All times 2 over n. Okay, so where is this headed? This is headed towards 3 sums. Remember, we can have, right, if I have these subtraction signs, right, I can divide this into 3 different summations. 3 different summations, right? Each with this 2 over n on the outside, right? N is sort of above the fray, doesn't matter. So I'm going to say this is 2 over n. 2 over n, we're going to distribute that as we do this, right? So k equals 1 to n of 15 minus 2 over n, k equals 1 to n, my summation signs are getting much worse, of 4k over n, minus again, this 2 over n, because remember, we have that on the outside, k equals 1 to n, of 4k squared over n squared. 4k squared over n squared. Do I agree with that? I think I do. Okay. So now let's pull everything we can outside of these sums. Remember, if we have the constant, we can pull it outside. So I get those nice little rules we have at the beginning of class, right? The nice little rules that were written on the left side of the board today. Okay. So if I want to pull, I can pull the 15 out and leave a 1 in there, right? So this is 30 over n times the sum of 1 gives 1 to n. Remember, that was an easy guy. Then here, I can't pull the k out, but I can pull the 4 over n out, right? So let's pull a over n squared times the sum of k equals 1 to n of k. Again, we know what that is. And then here I can pull the 4 over n squared out. I can't pull the k squared out. But I can say this is 8 over n cubed times the sum of k equals 1 to n of k squared. Well, these are just the 3 formulas we had at the beginning of class. Well, 3 of the 4. 3 of the 4 formulas. right? And remember, if I'm gonna, I'll circle all of these in different colors. So we'll have the blue sum, the red sum, and the green sum. Well, remember the blue sum is simply saying if I add up 1 n times, how many do I have, right? Of course I have n, right? I have n ones if I do that. So this is still 30 over n times just n, right? Well, what about the red sum? The red sum, I still have this 8 over n squared. Well, that's if I add up k, all right, from 1 to n, right? So that's 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. All the way up to n. And remember, that followed this form, right? That was n times n plus 1 all over 2. And then lastly, the green sum, right? The one that, again, we made the mistake with in class. We won't make that mistake again, right? That thing of k squared, right? That'd be 1 plus 4 plus 9 plus 16. That's n times n plus 1 times 2n plus 1 all over 6. And you're saying, oh, there's no way we're going to get 22 thirds. False. You're wrong, I think. Let's see what we get. So we're talking about the limit as n goes to infinity of these things, right? So we're going to sort of be only concerned about my front term, right? My leading term in each of these guys, not my subsequent terms. So 30n over n, well, that's just 30. This guy right here, this term, right, with the black and red here, right, I'm going to get 8n squared in the top, and I'm going to get 2n squared in the bottom. Do we see that? I'm going to get 8n squared in the top and 2n squared in the bottom. So that's really, right, I'll write that out, right? We'll write 8n squared, and we'll have another limit here so that we don't get confused. 8n squared over 2n squared, right? And then who cares what else is here, right? There's really some other terms here, but who cares, right? They're not the leading terms. Similarly here, right, I'm going to get 16n cubed in the top, plus, who cares, over 6n cubed in the bottom. Well, as n approaches infinity, that's just 30 minus 8n squared over 2n squared, that's just 4. And then this thing, this 16 over 6, right, that's really 8 thirds. So this thing is 26 minus 8 thirds. 8 thirds, right? Just a little bit less than 3, right? You guys will see, right? This is, in fact, 23 and a third. Whew! That was scary, right? That we thought we might miss that. So this is another example of what we did in class. So, I appreciate that you guys may have already stopped, or may have already, tried and struggled tonight, and I apologize for that. It certainly wasn't my intention, but if this video can help you make some sense of it either today or tomorrow, that would be great. All right, I will see you guys.